Okay, welcome back. So looking at some of our definitions around a wave. Now you notice how here's a wave pattern going on as it propagates through space. And when we look at this idea of wave, we have something called wavelength. We give the symbol lambda for wavelength. And it's just referring to like any of the same repetition points of a wave, like this is crest to crest right here, could be trough to trough. We call that wavelength. We have got our amplitude, which is this thing called the equilibrium position or the rest position of the wave. How far does the wave displace from that equilibrium position, call that amplitude. And then any random point of displacement of a wave, we just call that position, we give it the letter x. So using our ideas of the wave, we're going to go back and leverage into some past information that we worked with Hooke's law. So Hooke's law just says the force on a spring is proportional to negative kx. This is our spring constant, this is our stretch. And if you remember, we did this before, but we looked at this idea of the slope of the force versus stretch graph is what we call the spring constant. And the integral, or the area under the curve of the graph of force versus stretch, is what we call elastic potential energy. So we're going to use those concepts as we get into understanding simple harmonic motion. So simple harmonic motion itself is when you take some sort of a medium that is stable. And let's use the example of like a spring. So if you notice this spring right here, if it was sitting all by itself and not moving, it'd be in its equilibrium position. But if you were to apply a force and stretch it, and then let go, it's going to go into simple harmonic motion. And you can kind of see that happening right here on a mass spring oscillator. And now as you pull that force, the force is always going to be redirecting you back toward the equilibrium position, which is why we get the F equals negative kx. The negative is back towards that direction. But it's also proportional with this spring constant in mind. Notice that because force is proportional to stretch, you also have acceleration proportional to stretch because force is proportional to acceleration. So all those things kind of work out with our definitions. Now you're going to start messing with these things with two labs. And the first part of these two labs is going to happen in your journal. So get out your pendulum lab first, and you're going to mess with the pendulum. Just check out all the different tools that are in there. But you're going to start swinging the pendulum back and forth. And then all of these questions are going to ask you to mess with something and see what happens and come up with a qualitative answer. So this is all qualitative stuff here, and you're going to go ahead and put that in your journal. And then you're going to go to the mass spring oscillator FET, it's a different FET, and do basically the same thing and just kind of feel it out and see how is that working out for you. Now, once you're done with that, go ahead and check out our definitions and our formulas for the mass spring system and the simple pendulum, and then notice what matters and what doesn't matter when it comes to the time period of these types of simple harmonic motion. Going to give you some good hands-on experience. I've got the answers right here. Okay, so you can just check those out afterwards. Now, the next thing you'll do is jump into this pendulum FET, and you're actually going to create a test with a pendulum FET. And you're going to go ahead and test time, and you're going to put that versus the length of a pendulum, and you're going to do a linearization process. And so what I've done is I've created this sheet right here that you're going to use, and you've got time period versus length. So these are two things you're going to measure right here. This is going to be your independent variable, it's going to be your dependent variable. And then you're going to go ahead and linearize the data by looking at the relationship with time squared to length. So you're going to have to take these values, square them, and then you're going to be doing a little work with the pendulum equation, and I'll kind of show it. It's right here. There's the pendulum equation to linearize the data and then come up with the meaning of the slope. And because this lab was being done on the moon, you're going to actually go ahead and set the moon on there. You're going to find out what the gravity is on the moon and then confirm it and see if you were actually right. Very similar to what we did in the gravity lab that we did before. Okay. If you have any questions, there's a help. Oh my gosh, I don't know what's going on here. You can check that out for help too. Finally, you're going to end up with a quiz today. And don't forget the simple harmonic motion practice problems. I'm putting all the answers back here for you just to have it so you're ready to go. And there's attendance form for today, and there will be attendance form for the next class also. So look for the separate one that'll appear then. So that's it today. Everybody have a great day and enjoy yourselves. Goodbye.